and welcome to my presentation on my research entitled High Bandwidth Current Probing Techniques for the Dynamic Characterization of Wide-Bandgap Semiconductor Devices. I would like to begin my presentation with an example that you're all familiar with from your daily life, and this is a USB-C phone charger. This device is a power electronic system that converts the AC voltage from your wall socket into a DC voltage that's suitable for your smartphone. And if you touch this charger in operation, you will notice that it feels warm. And this happens because the device isn't 100% efficient. In fact, only around 90% of the input energy is transferred to the output, and the remaining 10% is lost as heat due to various loss mechanisms. First, we have the conduction losses, which are caused by the current flow. Then we have the component losses that are losses in electric components, such as capacitors or inductors. And finally, there are the switching losses, which are the focus of my work and occur each time a transistor changes between the off and the on state. To understand switching losses, we have to take a closer look inside the device. And the most common converter topology used in phone chargers is a so-called flyback converter, which is shown on this slide. The flyback consists of three main components. In the middle, there's a transformer with a diode and a semiconductor switch that controls the current flowing through this transformer. And by looking at the waveforms, you will see that this switch turns on and off at a very high frequency of often more than 100 kilohertz. And this enables a very compact design because the energy is transferred from the primary to the secondary side in small amounts. However, there's a drawback because each switching introduces losses to the system. And this brings me to the introduction of switching losses. An ideal switch is shown on the left side. There's the ideal off state, where there are no current flows and there's a defined voltage drop across the device, and the ideal on state, where the current flows freely and there's no voltage along the device. But unfortunately, such a perfect device doesn't exist in reality. So on the right, you can see switching in a transistor. And you can see that between the states, there's a transition where voltage and current overlap, and this causes power dissipation. The lower plot shows this power as a product of voltage times current. And by integrating the power, we obtain the switching energies, E on for the turn on transition and E off for the turn off transition. And these energies are crucial transistor parameters as they reduce the efficiency and generating heat during each switching cycle. Yeah, now that you're familiar with switching losses, let's explore wide bandgap semiconductor devices. Power transistors come in various technologies, and each technology is suited for specific applications. First, there are metal oxide semiconductor field effect transistors, in short MOSFETs, which are very versatile and the most common technology. Then there are IGBTs, which are used for high current and high voltage applications. And finally, there are high electron mobility transistors, in short HEMT, which are preferred for high-speed switching applications. And the different characteristics result from individual physical structures you can see here in combination with the different semiconductor materials. MOSFETs are typically made from silicon or silicon carbide. IGBTs are usually made from silicon, which is a much thicker drift layer. And we have HEMTs that can be made, for example, from very thin gallium nitride layers on a silicon carbide substrate. And this radar chart you can see on that slide compares the properties of the different semiconductor materials. The blue curve represents silicon, which has a relatively small electron band gap in contrast to silicon carbide and gallium nitride, which have much larger band gaps and are therefore classified as wide bandgap semiconductors. You can see that SiC and GaN outperform silicon in many areas, which makes them essential for efficient and compact power electronics. Wide bandgap materials usually offer higher operating voltages due to their strong breakdown field. They offer faster switching with lower switching losses, and they offer a better thermal performance that allows a reliable operation at higher temperatures. And this development can once again be illustrated using the example of a phone charger. On the left, you see a device with a rated power of 20 watts that uses silicon MOSFETs. And on the right, there's a similar sized device, but this one uses gallium nitride technology. And despite having almost the same size, The GaN-based charger delivers 6 times more power and also has multiple ports at the output. Yeah, the rise of wide bandgap devices is transforming many areas of power electronics, of course, not only phone chargers. And this graph shows different applications sorted by switching frequency on the x-axis and output power on the y-axis. In the bottom corner, we see consumer electronics like the phone charger or also computers, where GaN technology is particularly effective because of its high switching speed, where silicon carbide performs well in high power applications like renewable energy systems or industrial equipment because of its higher breakdown voltage in combination with a better thermal performance. There are also applications where GaN and SiC compete, and this is particularly in the field of electromobility. For example, in automotive onboard chargers, where the efficiency and power density is directly linked to the range of a vehicle. And to optimize such systems, you can see here, we need to characterize semiconductors and measure their switching losses. And this is part of the dynamic characterization from the title of my research. All right, this brings me to the first key topic of my dissertation, and this is the measurement of switching losses in the double pulse test. The double pulse test is illustrated by the circuit, where the device under test is typically a half bridge that's connected to a voltage source, with the switching node being connected to a load inductor. And while the high side switch remains turned off all the time, we control the low side switch using a gate driver. The test sequence is divided into 3 phases. The first phase is a current ramp-up phase, and in this phase, the low side switch is turned on, which causes the current IDS to increase via the load inductor. And once the desired switching current is reached, the switch is turned off, allowing us to calculate the hard switch turn-off event. And this includes measuring the switching transients that I have introduced before. After phase 1 comes phase 2, the freewheeling phase. And after the turn on, the current commutates to the high side switch in reverse conduction and maintains at a nearly constant level due to energy preservation in the inductor. Shortly afterwards starts phase 3, where the low side switch is turned on again, and this enables us to capture the hard switched turn on event because the load current directly commutates back to the lower path. And this entire test sequence typically occurs within a time scale of just a few microseconds and is called double pulse test because of the 2 current pulses you can see during phase 1 and phase 3. Yeah, this was the introduction to the double pulse test, but performing this test comes with several challenges due to the non-ideal nature of measurements. To measure the drain source voltage and the drain source current, we need to add probes to the circuit, as illustrated in the figure. And this is the voltage probe, which is connected in parallel to the DOT, and the current probe, which is connected in series with the DOT. And connecting these probes will change the switching behavior and leads to measurement errors because of the non-ideal transfer characteristics. On the right, you can see an example that shows the original signal VDS, that's the blue curve, and the probe response in red. And here you can see that 3 key issues stand out. The probe introduces a short delay, that's marked in green here. The probe signal shows a small overshoot, and you can see that the probe response has an increased rise time. The rise time is the time that the signal takes to rise from 10 to 90% of its final value. The suitability of a probe is determined by its bandwidth, and there's a rule of thumb that says that the bandwidth should always be greater than 0.35 divided by the rise time of the input signal. So in this example, the bandwidth of the probe is obviously too low. Okay, now let's have a look on available probes. And this slide shows the most prominent voltage probe technologies sorted by bandwidth. In the range of 500 megahertz, there are 2 solutions. First, we have passive probes, which are the most common probe technology, acting as a resistive voltage divider. The drawback is a relatively high input capacitance, around 10 picofarad, and the lack of isolation to the ground potential. Then we have high voltage differential probes. Those can handle very high voltages without a ground reference and offer a dynamic performance that's comparable to passive probes. In the range of 1 gigahertz, we have optically isolated probes, and these probes combine very high bandwidth with superior isolation. These probes are very expensive, but offer an excellent performance in the double pulse test. There are also probes for higher bandwidths that are single-ended active probes that are based on high bandwidth operational amplifiers. But unfortunately, these probes are usually limited to voltages below 10 volt and are therefore not suitable for double pulse test with very high drain source voltages. In addition to the voltage, the current must also be measured. And again, several options exist that you can see here sorted by bandwidth. In the range of 50 megahertz, there are Rogowski coils based on inductive measurement. These offer much flexibility, but are limited to AC currents, as sometimes are also sensitive to EMI because of capacitive coupling, for example. Another very interesting technology are optical sensors based on the Faraday effect. These promise an excellent isolation, but are relatively new to double pulse testing and have not yet been fully established. Up to 250 megahertz, there are current transformers with a closed magnetic core. However, these devices are usually too bulky for device-level measurements in the double pulse test and cannot assess currents that are on the PCB trays. And finally, we have coaxial shunts. These are specially designed resistors with a very high bandwidth up to 2 gigahertz. And the drawback of this technology is the parasitic inductance, that's approximately 2 nanohenry, which can distort the measurement and will show an impact on the switching behavior. So in conclusion, it looks like there's not a perfect solution for the double pulse test, and therefore we have always to expect systematic measurement errors. To analyze these errors, I developed a simulation model you can see on the slide. The model includes the complete topology of the double pulse test with added parasitic elements, the detailed behavioral models of the switches, and modeling of the non-ideal probes. The voltage probe is modeled as a parasitic capacitor with a low-pass filter and a delay element, while the current probe is modeled as a parasitic inductance and similar transfer limitations. And this allows us to evaluate the relative errors in the turn-on and turn-off energies of the DOT by comparing the ideal values. You can see them in blue with the distorted values here marked in red. And this model was applied to 4 devices, to 2 gallium nitride transistors and 2 silicon carbide transistors, all with different nominal voltages. And using a design of experiments, 250,000 setups per device were simulated by varying the key parameters of the model, such as the current probe inductance, the voltage probe capacitance, the bandwidth, but also the operating point defining parameters like switching voltage, current, and temperature. And this methodology then provides a sensitivity analysis and a deeper understanding of the error mechanisms. Today, I will focus on the results for the 100-volt GaN device, as this is the most error-prone device because of the fastest switching speed along the 4 tested devices. You can see the total error, which is broadly distributed, ranging up to plus minus 50%, which is extremely high. And to assess the influence of the individual parameters, I analyzed their main effects on this measurement error. And this involved grouping all simulations by a single parameter setting and calculating the mean percentage error for each group. And the plot shown on the right highlights the main effects of the parameter L probe on the mean percentage energy error at the turn-on. And you can see that between the minimum and the maximum setting for L probe, there's a difference of minus 28 percentage point, which is a very strong effect. You may ask yourself why there's still an error at 0 nanohenry, and this happens because all sources of error are superimposed in this view. This analysis can now be extended to all other measurement parameters, which allows to make some key observations. You can see that the current probe inductance is the dominant source of error, while the voltage probe capacitance and the voltage probe bandwidth have smaller effects. The measurement bandwidth of the current probe also plays a critical role and must exceed at least 500 megahertz to ensure accuracy. Another significant factor is the desk-queuing error caused by differences in the propagation times of the probes. However, this error arises during post-processing and can be corrected afterwards. So to reduce the overall measurement error, we have to focus on the current probe inductance and the current probe bandwidth. And this was the motivation for the following chapters of my work. At this point, I would like to give you a brief outline of the upcoming content. I have already introduced the double pulse test, and next I would like to present two solutions for current measurement. One is the design of an advanced resistive current sensor, and the other is the design of an advanced inductive current sensor. And as a proof of concept, both sensors will be tested side by side before I finish the presentation with conclusion and outlook. So let's begin with resistive current measurement. Shunt resistors are very easy to understand because in the ideal case, the voltage drop along a resistor is proportional to the current to be measured. In reality, there's a parasitic inductance, which, as we already know, must be minimized because it limits the bandwidth and impacts the switching behavior. And minimizing this inductance is a central objective for all shunt resistors. Yeah, shunt resistors are a hot topic with many innovative designs emerging. And this slide shows the most promising approaches from recent years with bandwidth on the x-axis and inductance on the y-axis. The simplest design is an array of surface-mounted resistors, and this is commonly found on evaluation board. Yeah, it's very easy to implement, but its bandwidth is below 1 gigahertz, and the inductance is also relatively high in comparison to the more sophisticated designs. Notable designs above 1 gigahertz include the UFCS shunt by Cambridge University and the SMD coaxial shunt from Keysight. There's also the impedance matching shunt, which offers an extremely high bandwidth, but is very difficult to implement. In 2023, I introduced the Radial shunt, which is a highly competitive design in this field with a bandwidth above 2 gigahertz. And on the next slides, I will present the latest variant of this design and show you its characteristics in detail. The design of the Radial shunt is based on several discrete thin film resistors arranged in a circular pattern, which creates a radial current flow from the outside towards the center. And this layout is key to a very good performance. Additionally, the resistors are placed directly beneath a coaxial connector, which acts as a shielding and ensures that there's no coupling when tapping the voltage. The entire setup is mounted on a multilayer PCB to provide a very short return path for the current, which keeps the inductance of the whole structure low. A key feature is the resistors being flipped upside down, as shown in the figure. Normally, the resistive film is on top of the substrate, so flipping the component decreases the current loop area and therefore reduces the inductance. And simulations show that the inductance remains below 100 picohenry at high frequencies, which is 20 times lower than conventional coaxial shunts and therefore a huge improvement. To evaluate the transfer function, the shunt is modeled as a two-port network. One port conducts the input current, while the other port provides a signal at the connector. And in this case, the impedance parameter Z21 corresponds to the shunt's transfer function as it's defined by the ratio of the output voltage to the input current. And I will address the assumption I2 is 0 a bit later. The transfer function is frequency dependent, but at low frequencies, we can expect a constant value, which is the shunt's DC gain. And by connecting 12 1 ohm resistors in parallel, a DC resistance of 83 milliohm is achieved. To measure the transfer function in the frequency domain, I implemented several prototypes on a characterization board to conduct measurements with a network analyzer. And in the first image, you can see the resistors before placing the connector. The other image shows the complete characterization board that enables de-embedding the shunt structure from the rest of the PCB by applying a SOLT calibration routine. The S parameters are then converted into impedance parameters, which allows extraction of the relevant Z21 parameter. And the graph on the right shows the measured Bode diagram of the transfer function. And you can see that there's a clear 3 dB cutoff frequency at 1.35 gigahertz and a relatively flat phase response. The next step was to examine how the termination of the shunt affects the transfer function. And in the first image, you can see the cascaded system with shunt, cable, and terminating resistor that's 50 ohm in the oscilloscope. And by using chain parameters, it's possible to analyze the entire system by multiplying the matrices of the single elements. And here it was found that the cutoff frequency slightly increased to 1.43 gigahertz. That's the blue curve. So cable and termination have a positive effect in this case. However, you can also see that beyond this frequency, the gain rises instead of declining, meaning that that is not a true cutoff frequency. So if the input signal will contain frequency components above the cutoff, these are amplified in the output and therefore will cause distortion. To address this problem, I designed a digital filter. The filter response is the orange curve that suppresses this resonance. The resulting system response is obtained by a multiplication of the shunt response and the filter response and is shown as the yellow curve. And you can see that this response now has a very clear cutoff frequency at 2.17 gigahertz, and this is considered as a shunt's final bandwidth. At the moment, this filtering is carried out in post-processing in MATLAB, but it may also be possible to implement this in hardware if it's necessary for the application. Another important aspect is the thermal capability of the radial shunt, which is a general limitation of all resistive current measurement. The small resistors used are rated for only 250 milliamp, which allows a nominal current of 3 amp in total, which would be way too low for the double pulse test. But since the double pulse test occurs over a very short duration, much higher currents can be applied. And to estimate the pulse current capability, I analyzed the resistors more closely. And you can see that the resistive element is the 4 microgram nichrome film on a ceramic substrate. And this element was evaluated using its specific heat and the energy dissipated during the test. And this allowed me to calculate a safe operating area, the SOA for the shunt, which is limited to a maximum temperature rise of 100 Kelvin, corresponding to an energy loss of 2 millijoule. The upper graph shows different current profiles of ramped currents within the SOA, and it indicates that pulse currents up to 100 amp are possible if the pulse length is not too long. And this makes the shunt suitable for double pulse test, but not for continuous current measurements. Yeah, this concludes the presentation on the resistive current sensor, and next I will introduce an inductive current sensor, which will act as a reference for the shunt measurement. One of the top performing inductive sensors at this moment is the Infinity sensor from Bristol University, which has a frequency range of 1 megahertz to 1 gigahertz and the parasitic inductance around 300 picohenry. The internal structure of the component is shown on the right, and you can see that the sensor consists of 2 pickup coils that are positioned on either side of the current to be measured and enclose part of the magnetic flux. So by the law of induction, changes in the current I sense will induce a voltage at the output, which allows the current calculation in post-processing. I aimed to replicate the sensor while improving its performance, and this was done by embedding the sensor directly into a PCB and customizing its geometry, which allows, for example, adding an extra winding. To optimize the geometry, I identified key parameters, such as the distance between the coils or the length of a coil, and used the design of experiment methods to generate multiple configurations. And the study involving 5 geometric and 2 material parameters produced 128 designs for simulation. And the analysis revealed that there's a trade-off between the sensor bandwidth and the gain. Smaller designs usually achieve a higher bandwidth but a lower gain, which is disadvantage for certain applications because of a lower signal-to-noise ratio. And the final design balances gain and bandwidth and features a compact design with 2 windings. Afterwards, I implemented a prototype of this design to measure its transfer function. And using a characterization board, it's possible to de-embed the sensor from the network analyzer measurement the same way it was done for the shunt resistor I showed you before. The transfer function in this case is derived by integrating the Z21 network parameter in the frequency domain due to the dI/dt dependence of the law of induction. And as shown in the Bode diagram on the right, there's a resonance at approximately 2 gigahertz that requires a damping resistor at the sensor's output. So I tested different configurations, and the 250 ohm, which is the yellow line, the design achieved a bandwidth of 2.33 gigahertz and a very flat phase response. And this is a very good performance and twice the bandwidth of the Infinity sensor, which was the reference for this design. Yeah, the next step was testing the sensor in the time domain using a current pulse generator. And the setup shown in the image includes a closed core current transformer that's used as a reference. And the upper plot shows the raw sensor output in the time domain for two different variants, the single and the double winding. And here you can see that the double winding has a higher output voltage. To reconstruct the current signal from the sensor output, three post-processing steps are required. Step 1 is the offset calibration to remove the DC component. This DC component is caused by capacitive coupling, and in this case is around 1 millivolt. Step 2 is the gain calibration to calculate the sensor's mutual inductance, which is very small and deviates from the simulation results due to manufacturing tolerances. And in this case, the gain is below 1 nanohenry. And then finally, we can do the integration of the output signal by using the previously calculated values for offset and gain. And comparing the post-processed signals with the reference measurement, we can see an excellent match. So these steps ensure an accurate measurement. Upon closer inspection, you can see that the rise time of the test signal is around 20 nanoseconds, which is fast, though not quite matching the switching speed of wide-bandgap devices. And this brings me to the final part of my research, which is the proof of concept. And both introduced sensors will now be tested in a double pulse test with fast switching devices to evaluate their performance under real conditions. Yeah, to compare the sensors, I designed a sensor evaluation board that includes both sensors in series, so they measure the same current. And the diagram here shows a half-bridge configuration with both sensors placed at the source contact of the low side switch. As a DOT, two gallium nitride amps are used, rated for 650 volt and switching frequencies up to 2 megahertz, so we can expect very fast switching transients. A critical requirement doing this was a proper board layout, focusing on minimizing the power loop inductance. And the circuit is implemented on a 6-layer board, which allows for a very small current loop area between layers 1 and 2. And the inductive sensor is embedded on layer 3. And this is important because now the sensor is on the same side of the PCB core and therefore has a better coupling to the current that I want to measure. The PCB was completely simulated to obtain reference values and achieve the power loop inductance below 3 nanohenry. This includes also the capacitors. Yeah, this slide shows the hardware setup for the double pulse test. The drain source voltage is measured with a passive probe, which requires a precise compensation process and has a desk queuing accuracy of approximately 100 picoseconds. The radial shunt is directly connected to the oscilloscope, while the inductive sensor is measured via another passive probe. The load inductor is a toroidal coil that's located on the backside of the PCB, and the circuit is powered by a high voltage source from an existing test bench, which also provides the gate control signal via optical fiber. And the test was now conducted at various operating points. And here you can see the results for an operating point of 500 volt and 20 amps. The upper graphs show the drain source voltage during turn off on the left and during turn on the right side. And you can see that both happen in less than 10 nanoseconds and have very smooth switching transients. The lower graphs compare the drain source current waveforms obtained from simulation, from shunt measurement, and from inductive measurement. And in terms of rise times, all transients align well, though there are some uncertainties that you can also see. And then the final step involves evaluating these differences and calculating the relative errors. Since graphical comparison of the transients offer limited insights, I decided to evaluate the switching energy errors for all operating points and visualizing the differences as heat maps. And in the left graph, you can see the measured turn-on energies obtained using the shunt and the inductive sensor. And the heat map shows the relative error between both measurement methods and demonstrates a very good agreement across all operating points. The average error is in this case just 1.38%. When comparing the shunt to the simulation, the error is around minus 3%, with the greatest difference to the simulation is seen when switching on at low current values. And the reasons for this are most likely manufacturing tolerances of the component and could also be explained by the frequency dependence of parasitic elements, which are very hard to model accurately. For the turn-off energy, the situation is a bit different. The shunt measurement shows realistic-looking results, while the inductive measurement looks a bit distorted. And this issue most likely arose from using a passive probe with a high input capacitance instead of a high impedance active probe to measure the sensor output voltage. So there's some potential for improvements. The error between the shunt and the simulation is in the same region as for the turn-on, and on average 3.4%. But at this time, the greatest error is observed at high current values. However, this is still a good result because the turn-off energy is about 10 times smaller than the turn-on energy. So errors in the turn-off energy contribute less to the total error. Yeah, and overall, the shunt proves to be very reliable and is therefore the preferred device for characterizing fast switching devices. Yeah, this concludes the proof of concept, and now I would like to present a brief conclusion and provide an outlook for further research. This slide summarizes the key contributions of my work. The first point is the analysis of the measurement accuracy in double pulse tests, where the current probe was identified as the main source of error, especially for gallium nitride devices. The second and main contribution is the radial shunt resistor, which achieved a bandwidth above 2 GHz and a parasitic inductance below 100 picohenry. And this is a huge improvement compared to the coaxial shunt, which has a 20 times higher inductance. For reference, I also designed an inductive current sensor that reaches similar bandwidth, that is twice the bandwidth of the infinity sensor, but is limited to AC currents because of the inductive behavior. Both concepts were validated in double pulse tests, and the results indicated that the radial shunt is the preferred sensor for measuring very fast switching transients of wide-bandgap semiconductor devices. Future research could focus on the assembly technology of radial shunt resistors. The current design relies on discrete resistors, so the next step could involve embedding thin film resistors directly into the PCB. And this would create a uniform radial surface and significantly improving the performance by enabling a more consistent radial current flow. Technologies for embedding resistive thin film layers below 100 nanometer into PCBs already exist, but they are currently offered by only a few very specialized manufacturers. So advancing this approach would require a dedicated research project and cooperation with these manufacturers. To conclude my presentation, I would like to revisit the radar chart we saw at the beginning, illustrating the material properties of various semiconductor materials. You're already familiar with silicon, silicon carbide, and gallium nitride, which are widely used in today's devices. However, there are other materials that may play a role in the future, and these include the ultra-wide bandgap materials such as diamond, cubic boron nitride, and aluminum nitride. And as you can see in the radar chart, these materials demonstrate superior properties, particularly in terms of bandgap energy, breakdown voltage, and thermal conductivity. And this indicates that there will be even more advanced devices in the future. So my final message is that it's not only critical to develop new semiconductor devices, but also to develop the measurement equipment that's necessary to quantify their performance. Yeah, that was the summary of my research. So thank you for listening,